Okay, in this class, what we are going to do, we are going to revise 2's complement and also the logical binary shifts and the binary addition is also a little bit. Let's study the 2's complement in detail. 2's complement is basically used to represent negative numbers. Previously, what we have studied only positive binary numbers, and in 2's complement, we are going to study about 8-bit values, 8-bit registers, you can say, that can store only 8 bits. So the 0 in the 2's complement represents the positive number, and if the 1 is represents a negative number if it is the leftmost bit. For example, this is 19. 19 has the leftmost bit as 0, so this means it is positive number. 4 has the leftmost bit is as 0, so this is also a positive number. The range of these numbers are -128 to +127, means the lowest negative number is -128. The highest positive numbers with 8-bit registers is +127, +128, +129, +150. They are out of this range, so they will not be represented using 8-bit registers. We will need higher bits like 16 bits for them. Positive numbers in 2's complement are same as normal binary. Leftmost bit is always 0 in positive numbers. Now, if you want to convert this 19, let's say if you have to convert this 19 into binary, there is one method for it. Let's do the 8-bit method. Let's do how we convert that using 8-bit binary. 128, then we have 64. We have to remember this sequence: 16 and 8, 4, 2, 1. If you are studying it directly, then I suggest you that you study this sequence, that we put 1, then double it 2, double it 4, double it 8. So there are total 8 values. Now what we have to do is these are basically the powers of 2. uh, 128, let's say which number is small of them is smaller than 19. So 16 is the number that is smaller than 19, so we put 1 with the 16. Now, what is the next number? 16 plus 2 plus 1 gives us the 19. So we will put zeros with these numbers and 1 with these numbers, and all the left bits will be considered as 0. Okay. Now if we have another number is 4 in the with this range, so let's represent the first number. This is 19, and let's represent the 4. 4 can directly be represented, so we can put 1 with the 4 and 0 with the rest, because as 4 is directly convertible, so this is how it is representing 4. Let's move forward. uh, let's see, convert binary, a positive binary number to binary. Let's convert another number, that is 38, into binary. So what we first do: 128, 64, 32, 16, 8, 4, 2, 1. We have to remember this sequence. In 8-bit numbers, this is 1, 2, 4, 8, or you doubling them. So any number that is less than 38, 38 is 32. Let's put 1 with it. Let's see another number that is close to it. 32 plus 16 becomes the number larger than this. 32 8 plus 8 also is larger than 40, is larger than 38. 32 plus 4, it is smaller, so we put 1 with it. 36. Now 36 plus 2, it's again 38. Now the number is equal, so we have found all the positions of the ones. Now we put the zeros with the rest of the positions. So this is how we have represented 38 in binary number. Now let's represent 125. So 125, any number that is closest to 125 is 64 among them. So we put 1 with the 64. And if we add this number 32, that becomes 96, and 96 is still smaller than 125, so we will put 1 with it as well. So next, what we have 96 plus 16, that is 112. It is still smaller than the original number. We will put 1 with it. The 112 plus 8, 120. We will still put 1 with it. 120 plus 4, 124. We still put 1 with it. 124 plus 2, 126. We don't put 1 with it, because 126 becomes greater than this number 125. So we now 124 plus 1, 125. So this is how 125 is directly converted into binary. Now let's see another example. There's now here what we have done, we have converted binary numbers into the denary numbers. I will do it very quickly. 1 2, 4, 8, 16, 32, 64. Add all of these values that are with ones. So we will get 110. Similarly, we can do it with this number 63. We have already studied it. If you want to study it in detail, you can go to lecture 1 and 2. Now let's say we have another method to we have to represent the negative numbers in 2's complement. The first method is the direct method, that is the same method. We use minus 128 column. The first column is minus 128, that is the most significant bit. Next is 64, 32, and 16, 8, 4, 2, and 1. Now the first value what we have, now suppose we have to represent minus 109. The first value we have is 1. So what we have, minus 128, we have minus 128 here. If we what we do the next, where we will put 1 next. So let's say if we do minus 128 plus 64, we have to convert minus 109. We have to write this minus 109. What we will do, we have minus 128 as the first bit. Minus 128 plus 64, that becomes minus 64. Minus 64 is much larger than minus 101. In negative numbers, smaller numbers will be larger. Minus 64 is much larger than 64, so we put 0 here. Again, minus 128 plus 32, that also becomes minus 96. That is also larger than that, so we will put minus 128 plus 16, that becomes minus 112. We will put 1 here because minus 112 is still smaller than minus 109. Minus 1, now we have minus 112 plus 8 becomes minus 104, that is larger than that, we put 0. Minus 112 plus, that becomes minus 108, so that is also larger than minus 109, we put 1 here. Minus 120, minus 112 plus 2, minus 110, then again plus 1, that becomes minus 109. This is how we have converted it directly into binary number. And let's say there is another number, there is a standard method. Let's do this minus 167 in the direct method. Then we will use this standard method, that is 2's complement. But first let's revise minus 167. We have the first bit minus will be considered as minus 128, then 64, 32, 16, and then we have 8, 4, 2, 1. So we put 1 here. Minus 128 plus plus 67. We will use the plus value of it. That is minus 128 plus 67. That becomes our okay. No. Minus 128 plus 64. That becomes minus 64. This minus 64 is larger than minus 67, so we put 0 here. Minus 128 plus 32, that gives us minus 96. Minus 96 is smaller than minus 67, so we will put 1 here. Minus 96 plus 16, that gives us minus 80. It is still smaller than minus 67, so we put here, that becomes minus 80. Minus 80 plus 8, that becomes minus 72, so we will again put here. Minus 72 plus 4, minus 68, that becomes again 1 here, and then we put here 0 and here 1, so that becomes minus 67. This will be the binary of this number. Now there's another method for that. I'm going to tell you another method that is called 2's complement. So what we do in the 2's complement, we convert our number to positive binary. How we convert to positive binary? We don't we ignore the negative sign first, and then we convert that. Let's say this is the number is minus 67. So to convert it into binary, we will only consider this value plus 67. So let's convert 67 into binary by the other method. 2 multiplied by 33, that gives us 66, and the remainder is 1. 2 multiplied by 16, and the remainder is again 1. 2 multiplied by 8, that gives us the value 16, remainder is 0. 2 multiplied by 4, remainder is 0. And 2 multiplied by 2, remainder is again 0. 2 multiplied by 1, remainder is again 0. And what we have, 2 multiplied by 0, and remainder is 1. So this is how we will write it. What we will write, 1 4 zeros double 1. We have 1, we have 4 zeros, then double 1. How many digits are these? 7. So the leftmost digit will be as 0. So this is a positive 67. Now in order to convert it, what we do the next step, we invert the bits. Invert bits means 0 will be converted to 1, 1 will be converted to 0. So now we are going to invert the bits, 1, and this will become 0, then all 4 zeros will become 1s, and then we become double 0. And what we do next thing, we add the 1 to it. If we add 1 to it, then this value will become 1 0 4 1s 0 and 1. So this number will represent our value minus 67. You can see, observe it from here. Here this value and this value is also the same. So this is how this number is converted by taking 2's complement. How we take the 2's complement? First, we convert the our number, its positive number, into binary. This is how we took 67, ignored the negative sign, converted into binary. We inverted the bits, then we added 1 to it. So this number became the representation of negative 67. Inverted, add 1. So this is how our number is represented. Let's say we have another number minus 79. How we convert it? By using the 2's complement. I'm going to again converting it by using the 2's complement. Let's do it with the uh, okay, let me see. If we 79, we would use 79 and we convert it into using 2 multiplied 39 gives us the remainder as 0. 2 multiplied by uh, what we have now, 19, gives us the remainder 1, as 39 is odd number. 2 multiplied by 9, remainder is 1. 2 multiplied by 4, remainder is 1. And again 2 multiplied by 2, remainder is 0. 2 multiplied by 1, remainder is 0. And we have again 2 multiplied by 0, remainder is 1. So we will write it in this order: 1 double 0 triple 1 0. So what we have, 1 double 0 triple 1 0, and we put 0 here. Now what is the next step? Next step, we invert the bits. So we convert 1 to 0 and 0 to 1, 0 1 1, 0 0 0 and 1. Next we have to do the last step is add 1 to it. Now we are going to add 1 to this number. Let's say we are going to add 1. 1 plus 1 gives us 0 is the sum, 1 is the carry. So 1 plus 0 is 1. And next we have 0 0 1 1 0 1. So this is the final number that is representing the 2's complement. 1 0 1 1 0 0 1 0. This is number is representing the value minus 79. Let's see. Add 1 1 0 1 1. Okay, let's see if there is a mistake in it or what. For me, the value is 1 0 1 1. Oh, okay, there is something. I think I've missed something. Oh, okay. I made a mistake here in conversion. So we divided by 39, 230 by 39, 78. The last value is 1. So this is how this number will be. We have, in the end we have 4 ones. Now when we converted it into inverted the bits, that became 0, and 1 0 1 1 0 0 1 4 zeros plus 1 will become 1 here. There will be no carry bit, or will become this here. So 1 0 1 1 0 0 1, that is our final answer. Okay, so the most significant bit is 1, so it is representing the negative number. 2's complement works for any number of bits. Okay, it works for even 4 bits as well. But if we are using 4 bits 2's complement, so for example this is 1 1 0 1, we have 1 2 4, and the most significant will be as negative minus 8. Minus 8 plus 4 plus 1, that will, so this number will represent as the number minus 3. So 0 1 1 0, and now if we have the number 1 0 1 0 1 2 4 and minus 8, this number will represent the minus 6 value. Okay, let's move forward. convert 39 to 8-bit binary. Let's convert 39 to 8-bit binary. I'm using both methods separately. Let's convert 39 to 8-bit binary. What we have, what we'll just remember this sequence: 64, 32, 16, 8, 4, 2, 1. Now the number that is closest to 39 and smaller than it is basically 32. We put 1 here. 32 plus 16 gives us larger than this. 32 plus 8 is also larger than this. 32 plus 4 is smaller than this. We put 1 here. 36. And then we 36 plus 2 is also smaller. 38 plus and 38 plus 1 gives us 39. Now this is the conversion of this number into binary. Convert to denary 2's complement. Let's say, so this is our number. Convert to denary 2's complement. Okay, this is our binary number. What we have to do, we have to convert it into denary 2's complement. Let's say if we have to take the 2's complement of this number, or what we have to do. Okay, okay, it means that this number is representing a positive number, and let's say what it means. It means that we have to convert it into denary. Okay. This number is representing the positive number, as this is a sign bit. So what we do, we convert it into denary directly. 1, 2, 4, 8, 16, 32, 64, 128. This 2's number, this is negative, but 0, it's 0, so that this won't be added. 64 plus 16, 80 plus 8, 88, that gives us 89 value. First bit 0 is positive, so this is converted. And next is convert minus 127 to 8-bit 2's complement. Let's say we have to convert minus 127 to 8-bit 2's complement. I'm going to first use the direct method, that is minus 128, 64, 32, 16, 8, 4, 2, 1. As I said, the most significant bit will be represented using negative sign, minus 128. So this value is negative 127, so this value will be considered as 1. So minus 128, if you add any of these values from 2 to 64, that number will become greater than this number. So we don't have to use the number that, so we will put zeros with all this. Now minus 128 plus 1 gives us minus 127. So this is how the minus 127 representing using 2's complement. So there is an so the method. Now let's do the 2's complement method for it. This was basically I did with the direct method. Now if we do the 2's complement method, what we are going to do, so we put 127 to, oh sorry, not 126, this is 127. 2 multiplied by 63 gives us the remainder 1. 2 multiplied by 31, again remainder is 1. 2 multiplied by 15, then again remainder is 1. 2 multiplied by 7, remainder is 1. 2 multiplied by 3, remainder is 1. 2 multiplied by 1, again remainder is 1. So this is how, sorry, this is how, triple one and one, and then we have 4 ones here. So what we have, 0, triple one, double one. So this is our binary. This is our number that is making 127. Plus 127. Now if we take the 2's complement, is in order to take 2's complement, what we do, we first invert them. We replace 1 with 0 and 0 with 1. It will become this and this. We have replaced these values with this, replacing zeros and ones, and now this is how it happened. Next, what we are doing, we have to do plus 1 with it, so the number will become again and plus 1, that will become this number. Oh, okay, 1 0 0 0 0 1. So this is how. Now see the steps. First step is we have converted plus 127 to binary, and then we have inverted the bits. We have converted 0 to 1 and 1s to zeros. The final step, we have added 1 to it, so this number becomes this. So this is our final answer. Now the first bit 1 is negative. This is another number. First bit 1 is negative. Convert to 2's complement to denary. Now in order, this is the first bit representing negative number. So what we will do, let me write these number triple one, triple one, 0, 1. We have 1, 2, 4, 8, 16, 32, 64, and most significant will be minus 128. Now if we when we add them, what we get minus 128 plus 64 minus 64 plus 32 minus 32 plus 16 minus 16 plus 8 minus 8 plus 4 will be representing minus 4 plus 1. So this number will represent minus 3. Find magnitude, and so the number so this number is representing minus 3. So this was the direct method. Now it is asking for the 2's complement method. In order to take the 2's complement, we first what invert these bits. Now 2's complement method, let me erase this one that I did with them. Okay, I'm going to erase this method. This is a number that we are going to now. Now using 2's complement method. What's the 2's complement method? We first invert the bits. Let's invert these bits. We have 4, 5, 6, and then we have 1 and 0. So now we have converted it by using 2's complement. We have inverted the bits. Next step is add 1. We plus 1 to it. So the number becomes 000 000 1 1. So this number is representing what? 3 in binary. Now this number, now the opposite of is positive, and so definitely this number is representing what? Negative minus 3 number, because its most bit is negative. So the 2's complement of negative number gives us definitely a positive number. So this is our first bit equals to 1, means this 2's complement is representing negative number. And next bit is we find the magnitude. When we find the magnitude of that number, that becomes and inverted the bits. So what we did, we inverted the bits and add 1 to it. So this number becomes plus 3. So this number is representing what? Minus 3 number. This number is representing minus 3. How we checked it? We took 2's complement of it and then converted 2's complement to denary number. That denary number is representing positive 3. So this 2's complement number is representing what? Negative 3. So this is the exercise that all the students must do and practice by the methods I've mentioned and I've taught in my lectures. So we will do the next part of the logical binary shifts. We will revise that in the next lecture. Thank you. Okay, I'm going to discard it and let's stop.